Our next presentation is from Cody Carrell, who is a second-year PhD student in chemistry, and he knew he wanted to study chemistry when he was a senior in high school, performing chemistry demos for elementary students. With his degree, he hopes to work at a startup diagnostics company. His title today is Delivering Bacterial Detection to the Point of Need.
Foodborne pathogens pose a major health risk around the world. In the United States alone, they're responsible for 9 million infections each year, which result in tens of thousands of hospitalizations and over 1,300 deaths. As their name suggests, foodborne pathogens are acquired through sources like contaminated meats, leafy greens, or your Chipotle burrito. One of the major concerns and difficulties in preventing outbreaks of foodborne pathogens is the lack of a reliable detection system for on-the-spot detection. Currently, if somebody would want to test their produce for a foodborne pathogen, they would need to take a sample, send it to a centralized lab where it would be cultured, or the bacteria that they're looking for would be grown for several days, and then complex analysis would be performed. That process can take days or weeks to complete, and at that point, the produce has made it to market, and a deadly listeria outbreak is inevitable. What I'm interested in, and what I've been working on the last year or so, is taking the complex chemistry that occurs in those centralized labs and shrinking it down onto a device that can be used at the point of care. Now, point of care devices, some common examples you may be familiar with are devices like a pregnancy test or a glucose sensor for diabetic patients. Those devices are popular because they are inexpensive, easy to use, and disposable. We're aiming to accomplish those same criteria with our device, which is why we decided to make it out of paper. Paper is a really nice substrate for point-of-care testing because it is inexpensive and easy to fabricate. However, more complicated testing on paper-based devices is difficult because you need to add multiple reagents to your sample, and that typically takes manual pipetting steps, which is not very conducive to fieldwork, and most average users wouldn't be able to perform that. To help alleviate that problem, we designed a 3D printed manifold that houses our paper-based device and allows for semi-automatic addition of reagents and eliminates the pipetting steps. A simple color change from yellow to red indicates the presence of the pathogens that we're looking for. And currently we're using it to detect salmonella in bird fecal samples. However, with a simple change of just a few reagents, we could easily be detecting other types of foodborne pathogens, so things like E. coli, listeria, or even viruses like the flu. Finally, and possibly most importantly, instead of taking days or weeks to complete, our process takes just 1 hour to get a definitive yes or no answer. Because of these reasons, we're excited and hopeful that this technology and this device will be used around the world in a short period of time. Thank you.